Hello everyone, my name is Sabira David and myself along with Brianna Zaret and Jacob Anderson will be presenting our research proposal on the impact of processed food consumption on gut microbiome diversity and metabolic health. The human gut hosts trillions of microorganisms. These microbes aren't just passive passengers. They play a key role in digesting food, absorbing nutrients, regulating the immune system, and even producing neurotransmitters like serotonin and dopamine. A diverse gut microbiome is essential for both metabolic and mental health. But modern diet, especially those high in ultra-processed foods, are a major threat. Ultra-processed foods are rich in sugar, salt, and unhealthy fats, but very low in fiber, which is essential for nourishing beneficial gut bacteria. Multiple studies show that high ultra-processed food intake reduces microbial diversity and harms gut functionality. What is metabolic syndrome? It's a cluster of conditions which include risk of heart disease, stroke, and type 2 diabetes. It is characterized by abdominal obesity, insulin resistance, dyslipidemia, and hypertension. NCEP ATP3 has given criteria for diagnosing metabolic syndrome. A diagnosis of metabolic syndrome is made when three or more of the following criteria are present. These are abdominal obesity, when waist circumference is more than 40 inches in men and more than 35 inches in women. When triglyceride levels are more than 150 milligram per deciliter, when HDL cholesterol is less than 40 milligram per deciliter in men and less than 50 milligram per deciliter in women. When blood pressure is more than equal to 130 by 85 mmHg and fasting blood glucose is more than equal to 100 milligram per deciliter. Why is this study needed? Nearly 45% of adults in US are obese, and many suffer from related conditions like high blood pressure, high cholesterol, and diabetes, all components of what's called as metabolic syndrome. Ultra-processed food have been linked to these health outcomes, but the question remains, are gut microbiome changes driven by ultra-processed food themselves or by obesity and comorbidity? We also ask, can we use the microbiome to predict who's at risk for metabolic diseases before symptoms arise? This leads us to our research objectives. Does ultra-processed food intake reduce microbial diversity? What happens when healthy people switch to ultra-processed foods? And can microbiome patterns predict metabolic risk?
So to address these problems, we're going to use two complementary approaches. First, we're going to use a cross-sectional study of 200 participants divided into 4 matched groups based on BMI and UPF intake. And second, a crossover feeding trial where 20 healthy participants from the low UPF group will try a high UPF diet for 2 weeks, followed by a washout, and then return to a low UPF diet. This design will allow us to observe direct effects of diet changes on the microbiome. In our cross-sectional component, we have 4 groups. Those with a normal BMI or BMI below 30 and are on a low UPF diet, those with a normal BMI and a high UPF diet, those with a BMI above 30 or obese with comorbidities and a low UPF diet, and those with a BMI above 30 who are obese with comorbidities and a high UPF diet. All these groups will be matched for age, sex, socioeconomic status, physical activity, and medication to reduce confounding variables. This will allow us to isolate the impact of UPF intake within and across different health statuses. In the crossover trial, 20 participants from the healthy low UPF group will first consume a UPF-rich diet for 2 weeks, and then go through a washout period, or period where they stop taking the treatment, which would be a UPF-rich diet, and then would go back to their low UPF diet that they had originally. This would cause each person to act as their own control, and that way we can directly track how UPF alters their gut microbiome over time. So in order to collect our data in our samples, we'll have participants collect their own stool samples at home using standardized kits, and those will be stored at -80 degrees Celsius for preservation. And then we'll also gather detailed dietary data using food frequency questionnaires and 7-day food diaries, along with clinical measures like BMI, blood glucose, and lipid profiles, those being their cholesterol, to track. So for our workflow, here's a breakdown of the tools and technologies we'll use in our sequencing and analysis pipeline. So we'll start with DNA extraction from the stool samples using the Chiagen Power Fecal Kit, which ensures high-quality microbial DNA from stool samples. And then for shotgun metagenomics sequencing, we'll use Illumina Novasec platform to capture all microbial DNA present in the sample, providing a comprehensive view of the microbiome. Once sequenced, we perform a quality control using FastQC, which checks for read quality, lengths, and adapter contamination. Then Trimomatic will be used to trim and filter out low-quality reads. And then to remove any of the host or participant DNA, we'll use and apply need data, which also includes additional pre-processing steps to ensure clean microbial data. For taxonomic profiling, we'll use MetaPhy-An4, which accurately classifies the microbial species. And then to explore the functional capabilities of the microbiome, Human N3 is used for metabolic pathway analysis. And finally, all the way downstream, we'll have statistical and diversity analyses conducted using QIME2, R, Python for visualization and interpretation of the results. Together, this pipeline allows us to generate high-quality, biologically meaningful data from our samples. For our hypotheses and expected outcomes, we expect to identify microbial signatures linked to high UPF intake, patterns that signal early metabolic dysfunction, clear evidence of how diet directly alters the gut microbiome, and potentially microbial profiles that serve as early diagnostic tools for metabolic disease risk. And then for each of these, we have our null hypothesis stating that nothing will happen from our study, that won't get any information or value, and our alternate hypothesis is that there will be some difference or some new information or some group of betas that will allow us to make predictions or more accurate assumptions about gut microbiomes in the future.
Okay, now moving on into potential limitations of this study. So a potential limitation of the study is the reliance on self-reported dietary intake, which could result in recall bias, where participants aren't exactly remembering what foods they ate and when they ate it. So we've addressed this by using a 7-day food diary in combination with a validated food frequency questionnaire to enhance accuracy and reduce recall bias. Those two pictures at the bottom there, the bottom left-hand side is an example of a food log. On the right-hand side would be an example of a food frequency questionnaire that we would implement. Additionally, the relatively small sample size in this crossover substudy may limit the statistical power to detect subtle microbiome changes. However, due to the crossover design, in which each participant serves as their own control, this helps to improve sensitivity to diet-induced effects by reducing inter-individual variability. And on the right-hand side is a kind of a picture of what that crossover design looks like. Now moving into the intellectual merit of our proposal. So we are integrating high-resolution metagenomic sequencing with a robust crossover design. And with this methodology, this study will directly test the causative impact of ultra-processed foods on gut microbiome architecture, and this will be independent of obesity-related confounders. Additionally, the inclusion of advanced machine learning for predictive modeling is expected to identify any microbiome biomarkers that may serve as early indicators of ultra-processed food-related metabolic dysfunction. And finally, this work helps to build upon and extend current microbiome diet research by moving beyond correlation into prediction and mechanism, therefore significantly advancing scientific knowledge. And then finally, for broader impacts, so the insights gained from the study have the potential to inform evidence-based nutritional guidelines and public health policies aimed at reducing ultra-processed food consumption within the general population. The development of non-invasive microbiome-based diagnostic tools could facilitate earlier identification of individuals at risk for diet-induced metabolic disorders. Long-term, this could reduce healthcare costs and improve health outcomes. We can also implement educational outreach around the gut microbiome and dietary health that will help shape health literacy and empower informed dietary decisions. And finally, this project will provide hands-on training in metagenomics and data science, helping cultivate the next generation of interdisciplinary scientists.